As we saw in the previous video, when you learn these reactions, you want to learn them both forwards and backwards. You want to see reagents and say, okay, I know what that would turn into. But you also want to see products and think, okay, I would know how to make that. How? I could just add this stuff together. So you want to know these reactions forwards and backwards. And we did some practice going backwards in the previous video for acid-catalyzed hydration. And what we're going to do in this exercise is think backwards for hydroboration-oxidation. And you'll see practicing going backwards like this will be really useful. It'll help you transition more easily into doing multi-step synthesis exercises. So they say, identify the alkyne you would use to prepare each of the following molecules via hydroboration-oxidation. So how can we make this? What alkyne would we need? And remember, you can form an aldehyde by treating an alkyne with first some sort of boron compound, followed by hydrogen peroxide and sodium hydroxide. 9-BBN is a safe boron compound to use all the time. Okay, well, redraw the molecule exactly as it is. And you know that what this does is the hydroboration does is it adds an oxygen anti-Markovnikov, so on the less substituted carbon of the triple bond. In other words, wherever you have an oxygen bonded, that carbon was once in a triple bond. And there's only one direction that triple bond could have formed in. We don't have any carbons to the right, so it must have formed to the left. Now this is not the final answer because this has a zigzag and that is the wrong shape, and the shape is crucial. So instead you can redraw this. When you get to the alkyne though, when you get to the alkyne, draw it as a line, a straight line. And that's that. You'd have the hydrogen coming off there. If you want to draw that, you're welcome to. If you don't, it's implied in the skeletal structure. So that is the alkyne that we can use. If we treat that with, let's say, 9-BBN, followed by hydrogen peroxide and sodium hydroxide, we end up with our aldehyde here. So you can see how you're going backwards. We say, how could I make that? And you're saying, this recipe here. Okay, let's try this one. Now, here, we don't have an aldehyde, so we could form the triple bond in either direction. So let's redraw our molecule. And here I have the double bond to the oxygen. So there are two places where you can form the triple bond. You see the double bond to the oxygen, you think, okay, that was one of the carbons in the triple bond that we need. But that triple bond could have been on either side of that carbon. It could have been to the left, or it could have been to the right. So what happens when you treat each of these with the ingredients for hydroboration-oxidation? You'll notice that both of the carbons here are equally substituted. They're both secondary on the left, and they're both secondary on the right. And because they're equally substituted, you will get two products in each case. So let's draw those sort of two possible products. Okay. So when we treat these with first 9-BBN and then hydrogen peroxide in sodium hydroxide, that would normally add a double bond to an oxygen on the less substituted carbon of an alkyne. But because these are equally substituted, we could either get the double bond to the oxygen on the right or on the left. And the same thing over here. We could either get it on the right or on the left of the triple bond. Well, these two molecules are very different here. This one is right against the edge, right? It's almost on the last carbon, and this one is kind of in the middle there. So those are different. But what you'll notice is that these carbons on the right are the same. Those molecules are the same. And the reason how you could tell that, even if you didn't take all this time to draw it out, is that this is symmetrical. You have the same number of carbons on both sides of that triple bond. And so because this molecule on the right only gives you one product, whereas this one on the left gives you two different products, this will be less efficient, and you won't want to do that one. You'll want to do the more efficient one, the one that only gives you the product you want, and that's this alkyne on the right. Now, if you just drew this as it is, it's technically wrong, because that molecule does not have that shape. So what you'd want to do is number this, 1, 2, 3, 4, 5, 6, and redraw it so that it's linear. So you could start with a triple bond if you want to. That is carbon 3 and 4. We know it's going to be a straight line on either side, so that's 2 and 5, and then we just need 1 and 6. So 1, 6. And that is the alkyne that we would use. In other words, if we treated this alkyne with first some sort of dialkyl borane, 9BBN is a good option, followed by hydrogen peroxide in sodium hydroxide, we would end up with this ketone. That ketone, which is a carbon double bonded oxygen with a carbon on both sides. So notice how we thought backwards. We didn't say, okay, what can I react this with? We thought, how can I make that? And we can make it from an alkyne. All right, let's try one more. In this one, redraw the molecule. We're thinking, how can I make this aldehyde? And then you see an aldehyde, carbon double bonded oxygen with a hydrogen on one side. And now you should start building an association. Oh, aldehydes, right. I can do that with hydroboration-oxidation of a terminal alkyne. So if you redraw this, you know that the carbon that has the double bond to the oxygen on it had to be involved in the triple bond. And there's only one other carbon that it's bonded to. So the triple bond must have been between those two carbons. In other words, this is your molecule, except you have to draw it so that it's linear. So you'd still have the two carbons there. They would just be linear. So notice 1, 2, 1, 2. So your final product is this one right here. If you were to treat this alkyne first with some sort of dialkyl borane, like 9BBN, followed by hydrogen peroxide in sodium hydroxide, you would end up with this aldehyde. So hopefully this gives you some sense of how you can work backwards. Whenever you see aldehydes, or even ketones, you could think, I could make that. I could make that using an alkyne and hydroboration-oxidation. And hopefully now you have some practice drawing the alkyne you would need. And again, you'll see this will be an important skill when you start to do multi-step syntheses.